Dear all, in this video we will be understanding the convolution integral and how it is used in Laplace transformations. So Laplace transformations with convolution helps us a lot when we see this convolution notation, and instead of making this whole integral, this is a definition of the convolution integral 0 to t f of tau g t minus tau d tau. Well, the Laplace theorem of convolution tells us that taking the Laplace of this convolution gives us capital F of s, g of s, and this is a very nice, useful method to solve differential equations using Laplace transform and convolution. It's not the only way, and it's definitely not necessary, but it will give us a good understanding of convolution integrals, and we're going to learn to solve Laplace transforms using convolution integrals. Here's an excellent question I'd like to go over. This problem is asking us to find this inverse Laplace transformation using the convolution theorem. And to remind you guys, I added the convolution theorem, which is Laplace of this convolution will be capital F of s and g of s. Notice how we would normally have a big integral for Laplace and all of that stuff when we wanted to do this. Well, the convolution integral, basically we are able to not do any integrals in anything and just find the capital F of s and g of s to find the Laplace. So the inverse Laplace of capital F of s, g of s will give us f convolution g. Okay, so if we are given this inverse Laplace transformation, we need to get the pieces of capital F of s and g of s. Do not use partial fractions, although, as I said before, partial fractions would definitely work and give you the correct answer, but if you're expected to learn convolution in your course, your professor might explicitly tell you to use convolution. So Laplace inverse. So the nice functions I can see here I want to pick up is 1 over s squared and 1 over s plus 1. Okay, and this is going to be at capital F of s, and this is going to be capital G of s. And then we know that the inverse Laplace of this part will be e to the minus t, and inverse Laplace of this will be t. Okay, so we are actually given that this is going to be equal to t asterisk e to the minus t. So we're going to use this method to simplify, find this inverse Laplace with the convolution theorem. And then everything is pretty simple. Now you only have to know the convolution integral to solve this statement. So from 0 to t, f of tau times g of t minus tau d tau. So to make sure, you can always check, like when you're in the learning process, you can check and it does confirm that this is the correct setup of this integral. So f of tau, well, I call the f function this one, and this one I call the g. Doesn't matter which one. F of tau, well, the thing is, it does matter kind of, because on the left you're gonna call the one tau, and the t minus tau should be on the right. If you switch the order, it's going to change the convolution integral a bit. So I would suggest both integral formulas, which are not really different, and then we're gonna build this integral. So f of tau, well, t is f of t, right? F of t equals to tau. I'm sorry, t, and f of tau would obviously be equal to tau. So tau and g of t equals to e to the negative t. So g of t minus tau will be equal to e to the negative t minus tau, and this will give you e to the negative t plus tau. Okay, so tau times e to the negative t plus tau d tau. Okay, so I understand some students will be like, oh, there are two variables here, what are we gonna do? Well, notice this. This is an integral, guys. Remember calculus 2. Well, in these integrals, we will only have one variable, the d variable. Okay, this is single variable calculus here. So what we're gonna do is we can actually pull this e to the minus t out, since everything's being multiplied with each other, and e to the minus t is just a constant. Treat t as a constant here. Okay, so I'm just gonna use some algebra to make this look better. So we're gonna say tau times e to the minus t, and then e to the tau. Okay, d tau. Well, pull this e to the minus t outside of the integral and get 0 to t tau times e to the tau. And this is actually a very commonly used integral in calculus and differential equations, t e to the t or tau e to the tau. And the way to solve this integral is going to be integration by parts. Well, the method I use is di method. Okay, so you're gonna put the one that derives and vanishes first. So t tau 1 0, and the integral will be e to the tau and e to the tau and e to the tau, because e to the tau will always be giving you e to the tau. And you do this plus minus plus, you do these multiplications, and the result of this integral will be tau e to the tau minus e to the tau, which is correct. I actually memorized this integral because it came up a lot, and I think it's useful to know, because sometimes in tests you can just know the integral, and you will just be able to save yourself some time. And then this e to the minus t is outside, so we should keep that in mind when we're substituting t for tau. And now we're gonna substitute, and our answer will be t e to the tau minus e to the tau for the integral, the first part of the integral. Always, I'm gonna keep this e to the minus t outside just to avoid any complications. And putting 0 for tau will give you 0, and e to the 0 will be 1, so minus negative 1. Minus negative 1, guys, because here's the thing, t, you're gonna put this and then you're gonna subtract it from the integral, and the negative from the e to the tau actually does cancel out with this other negative, which is gonna be making a positive. Okay, so finally our result will be e to the minus t times t e to the t minus e to the t plus 1 as your integral. And if you want to further simplify, you can just say t minus 1 plus e to the minus t as the result of this inverse Laplace problem.